Hello everybody, my name is Jad Beyhum and I'm currently a postdoc in KU11. Title of my talk today is a non-parametric instrumental approach to endogeneity in competing risk models. And this is a joint work with Jean-Pierre Florence from TU School of Economics and Ingrid van Kelegom, also from KU11. To present the problem that we face here, I will talk about an experiment, which is the health insurance plan experiment, which happened in the state of New York in the 60s. There you had 60,000 women between 40 and 60 years old, equally randomized into a control group and a treatment group. The women in the treatment group were offered the possibility to attend periodic screenings for breast cancer. Some of them refused, some of them accepted, so you have non-compliance. And what we are interested in is the effect of these periodic screenings on the duration before dying by breast cancer. Here you have two issues. First, the treatment is endogenous because of non-compliance. And second, you have competing risk because death by another cause prevents death by breast cancer from occurring. So this is the issue here. How do we estimate the effect of the treatment? And there are these two issues. We will develop a non-parametric model to do that. So let me now introduce the model. So you have a duration T and a cause of failure E. So this is, for instance, in our application, the duration until death, and this is the cause of death. And you have a treatment with categorical support. So in the model, you have some unobserved heterogeneity term, which is distributed as a uniform on the interval 0, 1. And it determines the potential outcome of the cause of failure, E of Z. If U is lower than PZ, then under treatment level Z, the cause of failure is 1 and otherwise is 2. Once it is determined, the duration until failure, T of Z, is also determined by two functions, phi1, when failure happens from cause 1, and phi2, when failure happens from cause 2. And you have this standard consistency condition. We have an IV, W, which is independent of U, and which will help us to solve the endogeneity issue. The duration T is right-hand sorted by a random variable C, which is independent of T given Z and W. And what we observe is Y, so it's the minimum of T and C, the censoring indicator, and the cause of failure when observation are not censored, Z and W. This is a graphical illustration of the model. So as I said, when U is lower than PZ, EZ is equal to 1, otherwise it's equal to 2. And then the durations until failure are given by the phi1 and phi2 function. Here you have the causal diagram. So W affects Z, but it's not affected by U and it does not affect U. So it's the reason why it's an IV. And also it does not directly affect the outcome. Also Z affects the outcome and U affects both the outcome and Z. So the causal effects of interest is the following. It's the effect of Z on the probability of failing from cause 1 before T. And this for any lowercase t. Remark that this effect is an average on all the population. And these things are what we call subdistribution function. So it's the effect on the subdistribution function. We could also consider effects on the cause-specific hazards or subdistribution hazard as well. So what are our contributions? First, we show that the quantities of interest in competing risk model, so I said the subdistribution function, hazard, and cause-specific hazard, so this, among which this main causal effect of interest can be directly derived from phi1. So we can just study the identification of phi1. We characterize the set of quantiles U at which phi1 is identified. So it's not going to be all quantiles. It's going to be only some quantiles. We provide partial identification results outside of this set. We outline an estimation procedure, and we give simulations on empirical application. So let's just talk quickly about the related literature. So for this problem, you either have some semi-parametric frameworks, so not non-parametric like ours, or you have frameworks that do not really estimate treatment effects on the full population, but only average treatment effect on the population of compliers. So population of compliers here are people, in the example of our empirical applications, those are the population of people that would accept the treatment if offered, but not all the population. So this quantity is interesting, but for instance, if we care about making compulsory such screenings, which for instance some insurance do, you have in some health insurance, you have to attend some screenings to be insured. Then what we may be more interested in is the effect on the whole population. So this is the first paper studying identification of the average treatment effect on the full population in a non-parametric setting. So how do we study this identification? So let us define Tj of Z, which is Tz when failure happens from cause G, and which is infinity otherwise. So it is some kind of duration with a mass at infinity which corresponds to failure from another cause. And actually we can see that T1Z is equal to phi1ZU, where phi1ZU is just phi1 when U is lower than PZ, and infinity otherwise. So this is a model which is quite well known in the econometrics literature, which is called the Quantile instrumental regression model. But you have two differences. First, you have these masses at infinity, which makes the mapping phi1 not strictly monotonous. And also the outcome is right-answered. So that gives more complicated issues. And that's why we have to actually study identification of this model. We make these additional assumptions. So the distribution of U given Z equals Z and W equals W is continuous with strictly positive density at an interval of this form. Independent censoring, and the upper bound of the support of the distribution of C given Z is equal to Z is the same as that of C given Z is equal to Z and W is equal to W. Then basically what we show is that phi1 solves this equation where S1 is some kind of joint density of Z and survival function of T1. But so we basically, when we can identify S1, which is not always the case because of censoring, then if there is a unique solution to this equation, then we know that phi1 is a solution. So that's basically how we identify the quantile regression function. So the main identification theorem is as follows: under technical and standard identification condition, which is already in Chernozhkov and Hansen on numerous other papers, plus all the other assumptions we made, phi1 is identified on an interval of this form, where UI has a complicated expression that we give in the paper. So how do we do estimation here? First, we estimate S1 by the Allen-Johnson estimator. Then we plug it in this system of equation and we solve it. So we obtain an estimator for this. Then we estimate UI by UI hat using an expression of the paper, and we use Bootstrap for inference. And we report only results where for the values of U at which we have identifications. So here are just some results from the simulation. So you can see that this is basically the estimate of the quantile treatment effect, and these are the 95% confidence intervals. You cannot see the true value on the graph because it's extremely close to the estimate. And then here you have a naive estimate that would assume that there is exogeneity, which is not the case. And this is the coverage of the confidence intervals. So just close to UI, it goes down a lot, but before it's almost nominal. So thank you for your attention. And if you have any question, I will be available during the question session.